Hello everyone, welcome to our talk, utilizing cross-gate CPU allocation to exploit preempt-disabled Linux kernel. Before we start our talk, let me introduce ourselves. I'm Mingi, the vulnerability researcher of Theory. I'm currently researching the Linux kernel and participating bug bounty programs such as Kernel Step and Preempt-Disabled. And this is Wongi, the researcher of Theory DreamHack team. He also participating the Kernel Step recently. Today, we're gonna talk about two Linux kernel exploits along with the cross-CPU allocation. The first one is the bug found in NF tables, and the second one is the bug found in the traffic control subsystem. These two vulnerabilities are exploited using cross-CPU allocation on both slop allocator and body allocator. We exploited these at Preempt-Disabled 2023 and Kernel Step. Let's give a brief introduction to Kernel Step. Kernel Step is a vulnerability reward program focusing on the Linux kernel exploits. Its goal is to exploit vulnerabilities in the Linux kernel to access flag store on the server. Kernel Step operates across 3 kernel versions: LTS, long-term, support, cost, container-optimized OS, which is used in the Google Cloud, and mitigation. The kernel version is regularly updated on a cycle ranging from 1 to 4 weeks. Exploiting all 3 instances successfully, we can get a reward of over $100,000 for a single vulnerability. Now, let's talk about the first vulnerability. The first vulnerability is this. It was found in NF tables, and I exploited it in Preempt-Disabled 2023. And I was also successfully exploited it in the mitigation kernel of Kernel Step. To exploit this vulnerability, I used a technique called cross-CPU allocation, which is the subject of this talk. Before we dive into the details of the vulnerability, let's see the NF tables. NF tables is a Linux kernel packet classification framework. It allows us to intercept packets as they are input, output, or routed, facilitating the evaluation of a predefined set of rules. NF tables objects are managed by a batch system, allowing users to create, remove, and carry on objects such as table, chain, or rule by passing a series of batch commands to the kernel. When the batch command is sent to the kernel, it triggers a call to a predefined callback function. In the kernel, batch commands progress through prepare, commit, and release phase, while error handling takes place during the abort phase. In the prepare phase, NFT transactions are created based on the requested batch commands. This NFT transaction is subsequently used in the commit and release phases. During the prepare phase, NF tables objects are allocated, added to the list, and their reference counters are updated. For the delete command, requested NF tables objects are deactivated, but they are not removed from the list at this time. During the commit phase, the created transactions are traversed and batch commands are processed. If a delete command is encountered, the corresponding object is removed from the list. In the release phase, the NFT objects are free. Okay, now let's talk about the vulnerability. I discovered it by comparing 3 lookup functions of NFT chain. There are 3 functions implemented for looking up NFT chain, and the vulnerability existed when using the chain's ID for the lookup. Let's see the lookup functions of chain. The lookup by name function and the lookup by handle function calls the NFT active chain mask to check the activation status of the chain. It only returns the chain when the status is active. However, in the lookup by ID function, the NFT active chain mark is not used, so it doesn't verify the chain's status. As a result, it can return a deactivated chain that is currently being deleted, resulting to a used after free vulnerability. Let's turn this bug to UF situation. To do this, we pass the batch commands to the kernel using a send message as shown in the slide. Create two chains, delete the chains, create a rule, and delete the rule. First, create two chains, trigger and vulnerable. The trigger chain will store a pointer to the vulnerable chain, and the vulnerable chain is the UAF target. After creating these two chains, we delete the vulnerable chain. This results in the chain being deactivated in the prepare phase. We then create a rule with an immediate expression to reference the vulnerable chain. Deactivated chain should not be referenced, but due to the vulnerability, they can reference. And if we delete the rule, the reference count of the vulnerable chain goes to 0 in the prepare phase. So the vulnerable chain can be destroyed in the release phase. In the release phase, the vulnerable chain is freed first, and the trigger rule is destroyed. At this point, the UF is triggered by referencing the chain that was freed when the immediate expression is destroyed. The NFT immediate destroy function that triggers the UF is implemented like this. It reads data verdict chain and calls the NFT chain is bound function with it as an argument. Since chain is free at this point, the UF read is triggered by referencing the freed chain. Now, it looks like we can easily exploit the vulnerability. It appears that we can exploit this by spraying a fake chain after the chain is free, but before the rule references the chain, so that the fake chain is referenced when the rule is free. Sadly, this was not as easy as I thought it would be. The first problem I faced with this exploit was that I was unable to preempt the process to spray victim chains between chain destroy and rule destroy. Releasing NFT objects is done by the destroy worker, which is not preempted by other processes normally. So, spraying on one CPU is difficult. We come up with a way to spray objects on different CPUs. However, this method also failed to spray the victim chain. The reason is that objects freed on CPU 0 are returned to the slab of CPU 0, and objects allocated by CPU 1 are taken from the slab of CPU 1. Therefore, no matter how many objects are allocated on CPU 1, the freed object in the CPU 0 slab is not sprayed. To address this issue, let's take a look at the Linux kernel's slab structure. You can find more about the slab in Jaden and David's write-up and Andrei's talk slab internals for exploit developers. This is a simplified structure of the Linux kernel's slab. First, there is the K-man cache. It is divided into K-man cache CPU and K-man cache node. The K-man cache CPU manages a slab for each CPU, and it has a pointer of the active slab that is currently allocating objects. And it has a partial slab where allocatable objects exist. The K-man cache structure is implemented like this. We can see that it contains per CPU slab, and node. In slab, objects are allocated in several steps. First, it allocates the objects from the free list of the pulse view slab. Then, if no object is available in the free list, the objects are allocated from the active slab. If no allocatable objects exist in the active slab, it allocates an object from a pulse view partial list. And if the object does not exist in the pulse view partial list, it allocates objects from the node free list, not the pulse view slab. Finally, if allocator hasn't allocated an object up to this point, it creates a new slab. Now that we have seen how slab works, I'd like to introduce the cross-CPU allocation. The goal of cross-CPU allocation is reallocate a freed object on a CPU other than the one that freed it. For example, an object freed on CPU 0 is reallocated on CPU 1. To do this, we manipulate the cache. Assume the cache is configured like this. First, free the objects corresponding to the target cache, creating a partial list of CPU to free the target object. Then, freeing the objects that need to be reallocated. At this point, the freed objects are put into a partial list. Afterward, if we free more objects, the partial list becomes full. And the full CPU partial list is moved to the node partial list. Now, the UF object is available for allocation on other CPUs. Let's allocate an object on CPU 1. When we allocate an object on CPU 1 and exhaust the CPU 1's per CPU slab, the allocator fetches slabs from the node partial list to per CPU slab. We added a dummy partial slab previously because allocator leaves a minimal number of slabs on the node. Finally, if we allocate an object from CPU 1, the UF object will be allocated from the target CPU's per CPU slab, which means that a cross-CPU allocation is achieved. Now, we can reallocate an object on CPU 1 that is free on CPU 0. So it looks like we can now exploit using this technique. Let's follow the exploit using cross-CPU allocation step by step. First, we free some chains to make the partial list on CPU 0. We need to create some partial lists at this time because the allocator leaves a minimal number of partial lists in node when it moved from the node partial list to the per CPU partial list. Next, we freed the object that causes the UAF. Making the slab containing the vulnerable object is stored in the per CPU partial list of CPU 0. Further freeing of the chain causing the per CPU partial list of CPU 0 to become full. When the per CPU partial list is full, the target object is moved to the node partial list. Because the object is moved to the node partial list, now we can allocate the target object from a CPU 1. Next, when we spray victim chain on CPU 1, it first allocates objects from the per CPU slab. Then, when there are no available objects in the CPU 1's slab, it allocates an object from the node partial list. As a result, the target object that was freed on CPU 0 is reallocated on CPU 1. Then, we subsequently destroy a rule that references a free chain, the destroy function references the spread victim chain. Thanks to the cross-view allocation, we can now spread the victim chain before destroying the immediate expression. For the exploit, we make the chain to double free. To do this, we free the victim chain from the immediate destroy function and free it again on CPU1. The immediate destroy function calls the chain destroy function if the chain is bound. For a chain to be bound, the NFT chain binding flag should be set on the chain. The chain destroy function frees not only the chain object, but also the size controllable objects named name and udata. We use these two objects to leak and to control RIP. When the chain becomes double free, these two objects also become double free. We perform the exploit by spraying the necessary objects between these double free. First, the information leak. We leak the kernel text address to bypass kernel ASLR and the heap address to store fake ops. We spray the NF table's udata on the freed chain's name and free the table's udata with double free. Then, spray the target object with the information we want to leak and read the table's udata to leak the information. The information leak was done using namespace objects in the Linux kernel. Namespace is a feature of the Linux kernel that partitions resources and is used for things like containers. These structures were suggested by my colleague Kwang-Hoon Jung, who presented at HEXACON yesterday. Among the namespace structures, there are 3 available in the kmalloc CG caches: cgroup namespace, mount namespace, and IPC namespace. I used the cgroup namespace for leak. We can see the structure of cgroup namespace bottom of the slide. NSCommon has an ops address to leak kernel's text address, and the user ns ucounts and root cset stores the heap address. The cgroup namespace is allocated in the alloc cgroup ns function, which is called when the cgroup namespace is created. So, to spray the cgroup namespace, we call the clone with clone new cgroup as an argument. After executing the clone, we read tables udata to get the address of ops to bypass KASLR and read the ucounts to store fake ops. Now, we have leaked the information we need for our exploit. All that's left is to control the RIP to perform the rope. RIP control is done using the NFT rule object, which stores the NFT expression. The NFT expression contains the ops address of each expression. Since the ops is used when we control the expression, we can control the RIP to any value we want by changing the ops to the heap address we leaked earlier and creating a fake ops at the leaked heap address. We use the deactivated function of NFT expr ops, which is called when we remove the expression. Lastly, we create a fake rule like this, overwriting the address of ops with the address of ucounts leaked from cgroup namespace. Because cgroup namespace is freed when the process created by the clone terminates. we can use this address as the fake ops. We store the stack pivot gadget at the offset of the deactivate function of the fake ops, and use the push RX, pop RSP, pop RBP red gadget that pivots the stack to the beginning of the fake ops. Once the stack is pivoted, the row payload overrides mode probe path, and finally, we can successfully obtain the root shell by triggering the mode probe. With the cross-cache allocation, we were able to obtain a root shell on Ubuntu 22.10, which was used in Pontoon 2023. This vulnerability is also exploitable in the mitigation instance of kernel CTF. The initial mitigation instance had kmalloc split file size and slap virtual applied. Config slap virtual is a mitigation against cross-cache attack that reallocate freed objects from other caches. However, cross-view allocation reallocates objects of the same cache to different spheres, so the exploit was possible regardless of the mitigation. So we successfully got a flag on the kernel CTF kernel.
Bonjour, everyone. Now I'll say about the CV 2024-36978, and which was used in the mitigation of the kernel exploits at the kernel CTF. This vulnerability occurs in TC, which stands for Traffic Control Subsystem. TC is responsible for managing the speed and order of packets, and it is managed by QDisk, a simple pivot queue that handles the context of those packets. Then, let's see the root cause. In this commit, we can see that queue bands have been changed to queue OPT bands. Why is the commit problematic? Let's examine the function. The code retrieved queue OPT band, but instead of using this variable, it used the queue bands. And before entering the loop, it modifies queue bands to queue OPT bands, and then proceed with the loop. If queue band and queue OPT band are different, it can lead to out-of-bound access, and actually, we can make it different. So we can get a slap OOB. Before entering to the exploitation, this exploit takes place in the KCTF mitigation kernel. It is essential to understand the following mitigation to grasp the subsequent context: kmalloc split file size, slap virtual, and random kmalloc caches. So I will simply explain about it. First, kmalloc split file size. Check the size of kmalloc using built-in constant p. If the size is constant, it uses the kmalloc size slab. Otherwise, it uses the dynamic kmalloc size slab. This separation of object commonly used in exploit, and the static size object make exploitation more difficult. If you see the Linux kernel code, there are kmalloc and built-in constant p. If the built-in constant p size is constant, they use kmalloc slab, and if not, they call the __ kmalloc, which allocate the dynamic. Next is slap virtual. Slap virtual is a technique to design prevent cross-cache attack, ensuring that slap virtual memory is never reused for a different slap. So generally, the exploitation uses these cross-caches, but it is impossible in the kernel CTF environment, kernel CTF mitigation environment. And last is random kmalloc caches. Random kmalloc cache exists for size ranging for kmalloc rand 01 to kmalloc rand 16, complicating each slap spraying. By receiving the return instruction pointer, which names read IP, that calls this function, and it determines which slab to use the band on each return IP. Let's see from the code. If you see the code, you can check that the index are determined from the return IP and hash value. So it is hard to successfully display. The probability is 1/16. Then how can we bypass this mitigation? How about use the body allocator? Because those mitigation implies to the slab, not body. So if we can allocate from the body, those mitigation or all will be bypassed. And if you see the kmalloc code, you can see the kmalloc max cache size. If over the size, they use the kmalloc large. Then kmalloc large calls the kmalloc large node, and it allocates the alloc page node. So alloc page nodes get chunks from the body allocator, so we can bypass all mitigations. It is simple, right? Then let's recall our vulnerability. First, we can get slab OOB right because of misusing Q bands and QOPT bands. And then free or QDisk. Actually, QDisk put not only do about the Q free or QDisk, but let's say it as a simple. Then what if we can context switch between those steps? First, allocate chunk, which name is removed. After that, OOB write, executed, and then context switch to 2. By using the some allocation with the k-string dupe, we can override QDisk pointer as the some value. Then we can override the QDisk pointer as the A, what you overwrite. After that, come back to context 1 and call QDisk put. The QDisk put access to the AAA, which was the overwrite. So we can set arbitrary pointer to the QDisk put. There needs one more technique to make some contiguous page from the body. It is possible? Yeah, it might be possible because body allocator usually return contiguous chunk after heap draining, but only if process use the same CPU. It is the problem. So there are two options exist. Find a way to use same CPU from different context, or make the body allocator return contiguous chunk even in different contexts use different CPUs. But we will second technique. Because there are preempt-disabled and there are no log or RCU between steps. Let's see body. If you see the body, there are per CPU also like this slab. Node data per CPU page set has each list of the body. So the order of page are allocated from those lists. Let's think about this situation. First, drain all per CPU body from CPU 0 and CPU 1. After that, allocate a bunch of chunks. I choose at the 300, but it could be 400 or 500 also. Then free all odd indexes chunk. And if too much chunk in per CPU, body sends chunks to the global free list. After that, CPU 1 gets some chunk. Those things are get from the global free list, so CPU 1 get chunk from the global free list. Then it can get index to n+1 to n+3 to odd numbers. Now, CPU 0 have even index chunk, and CPU 1 has odd index chunk respectively. So we get contiguous page to different CPU. Let's come back to the race condition. Where is the kernel address leak? We can override QDisk pointer, but we don't have any kernel address leak, right? Because SMAP, kernel only read-write itself address. So if you write user end address to the QDisk pointer, kernel will be panicked. And I use some trick, which is the mitigation kernel is still use the 6.1.55. This version still have fixed kernel address space, which is called the CPU entry area, as short, CEA. The most important thing is we can write arbitrary data on there, but it is patched in the recent kernel. So it is impossible to use the use the LTS. Then, how can we write the data on CEA? When process trap or panic, the kernel copy some register value to the CEA and set some register value and trigger trap. Those values will be written to the CEA. There are one problem, but I will say in the later. The important thing is now we can get some writable kernel address. So if we set to QDisk pointer at the CEA address, we can make the fake QDisk pointer, or we can set it QDisk pointer, what you want. Let's analyze QDisk put to exploit, which is RIP control. First, QDisk flag not be TCQF built-in, and also ref count would be 1, because we want to call the QDisk destroy. After that, we want to call the QDisk reset, because QDisk reset has the OPS pointer and access to the OPS pointer, so we need to bypass all those functions, like the QDisk hash deal or QDisk push step. Let's see. First, QDisk hash deal and QDisk push step are those functions, so QDisk flag must be TCQF ingress, and tap must be null. Also, gen kill estimator would be null, so rate est must be null also. After that, we can access to the QDisk reset, and QDisk reset access the OPS. After that, call the reset. So the condition is what you see it. And if you set OPS and OPS reset like this, we can control the RIP. So this is the draw. The flag, OPS tap, rest est, ref count, and reset are set. Then, how can you get the executable kernel address? We can call any address, but kernel has the KAS error, so we can't call anything. The kernel CTF enabled the disabled the KPTI, so we can use the entry bleed technique. Entry bleed is the size channel to get KAS error, which is introduced in HASP23. Now we can case space simply. Then let's do the stack pivoting. RBP holds the CEA plus hex to 0. So if we set the reset as the move RSP, RBP, pop RBP, and return, we can make some fake stack. So fake stack work like this. So HList BK would be new stack address. Now we can do ROP, right? But it is hard because fake stack is too small for exploit because of QDisk boot check. And I found some interesting gadget in the Linux kernel, which name is wakeup_long64. The saved store exists on kernel BSS section, so saved RSP, RBP, RDI are the variable in the kernel BSS section. And what if we can write some value of the saved store and call wakeup_long64? All register would be set it and call arbitrary value is possible. So I say a simple idea as the wake ROP. Let's say that fake stacks said like this: pop RDI, RSI, RDX, RCX, and wrote the user and fake stack, saved address, and the size. After that, we can call copy from user. The kernel copy user and fake stack to the saved stores. After that, we can call the wakeup_long64 plus some address. We can make some more huge size of fake stack. And we can call arbitrary value. Now, we can do ROP. It is simple. So now we can get the exploit. There are last simple problem, what you want to say the future. We need 3 CPU, but kernel CTF provide only 2 CPU. The first CPU needs to be OOB. The second CPU needs for the spray, and last CPU needs to be for setting the CEA, because CEA needs trap or panic infinitely. But if you run this code at the 2 CPUs state, it's just like this. Infinite loop for CPA hold all CPU1, so we can allocate 300 chunk, or the overwrite all bit QDisk PTR is impossible. So I thought that, one more race condition. How about set the CEA with the sleep? Just set CEA and sleep 4 microseconds, or nanoseconds. So, and how, if you do like this, the drain CPU per body and allocate 300 chunk, after that, free list index chunk, and allocate 300 chunk, after that, allocate orbit chunk, then set CEA between those conditions. Then, this is the ideal race condition as follows. It is same as 1 to 5 and OB. Overwrite the OB QDisc pit here and just set CEA. Then we can satisfy all the conditions, so after call the QDisc put, we can get some control. And this is the result. I think you're interested about it because this race condition would be possible. Because there are so many conditions or so many race conditions between it, so I provide some demo. It is just doing the copy file from the kernel CTF environment. And after that, you can get a kernel CTF flags. And this kernel CTF flag is available to the current state, so please do not write these things to the docs. Yeah. And sorry. This is our conclusion. We exploit the CV 2023 31248 and CV 2024 36978. Cross-CPU allocation is effective for reallocating objects on different CPUs. The mitigation in the kernel prevent cross-CPU attack, but cross-CPU allocation using the same slab cache is still possible. It could be slab, or it could be body. And if you have more questions, you can ask here or contact to those addresses. Thank you, and mercy, and 감사합니다.